All right, in these problems, we have to come up with a power series and then determine the interval of convergence for it. Now, it lets us know that our center is A. So for our first problem, A is 1, but all the others, A is 0. So those probably the 34 and 35 will be a little easier to manage as far as that goes. So it gives us this note that, if you recall, this is a geometric series here. So we have this converging to that. It's given us the fact that this particular one here for xn has an interval of convergence of -1 to 1, so we're going to use that. And let's take a look at number 33. So we're given f of x is 1 over x, and they give us this hint. We can break up that value. We can take a 1, minus 1, and so forth. So what we want to do is return that. Here our A is going to be 1, and that's clearly what we're going to have here. So this, either that or this guy here, is going to equal the sum n equals 0 to infinity of 1 minus x to the n, because that's what our 1 is there. Or that's what our x is. Instead of x, it's 1 minus x. So that's what we have there. To find the interval of convergence, so the interval, we take 1 minus a -1, and we take a 1 minus 1. And so what we get here, this one goes to 2 and this one goes to 0. So our interval of convergence goes from 0 to 2 instead of -1 to 1. Let's take a look at 34. All right, so we've got this x squared, this guy here, again, simply is equal to this sum. It's going to be x squared to the n, because what we have there is x squared. So this is equal to x to the 2n. And we can use the interval of convergence or the ratio test to find that convergence level. So do we use the ratio test? So limit as n approaches infinity of absolute value of x to the 2 quantity n plus 1 over x to the 2n. So here that equals limit as n approaches infinity. Well, that's 2n plus 2 minus 2n. So that's going to be just x squared, it looks like. Okay. So I'm taking a limit of x squared. This has got to be strictly less than 1. Which means our interval of convergence is going to be the same, -1 to 1. All right, so we see it works. As long as that's less than 1, we're good. And that only works for values between -1 and 1 for x, because again, we're squaring them. All right, let's take a look at this last one here, number 35. All right, so this equals, so we have an equal to there as well. That equals the sum, the same thing as we had before, only we've got an x here as well. All right, so if you recall, this is going to be x times this x to the 2n. Well, that equals x to the 2n plus 1. We can use the ratio test again. Limit And here we have x to the 2 n plus 1, all plus 1, over x to the 2n plus 1. And that gives us, let's look, 2n plus 3 over 2n plus 1. Or x to those values. So then we come down and that equals, when we subtract, we have x squared again, it looks like. And we're going to have the exact same interval again. So this is x squared has to be less than 1, which means our interval is again that same -1 to 1. And this is kind of the reverse procedure with some of these things. We have to turn it into a series before we can actually evaluate the series. But that's what this group of problems does.